Hey guys, it's time. Jumping ahead to chapter 6. Chapter 5 is about the X ray tube itself, but I don't think just another critique of the authors here, Carlton Adler Balak. Um, you don't teach them electrodynamics and it's just the order of the topics, really. You don't teach them all that and then skip ahead to the X ray tube and not explain the circuit schematics. So you talked about motors and transformers and rectifiers and all that stuff in chapter 4. Put it all together. So my critique is just a suggestion. Chapter 6, covering the X-ray circuit schematic, should be immediately following the content of chapter 4, and that's the way I've done it for my course. And that's why we're jumping ahead from chapter 4 to chapter 6. I guess, and again, I understand the difficulty of writing a textbook and getting everything right because you don't want to make errors, and then presenting the ideas in what you think is an orderly fashion, and then someone comes along and says, "Well, you really shouldn't have done it that way." Well, also I do acknowledge that writing a book is tough, so. Um, but for my course for radiation physics here at Nashville General Hospital, we are going to jump just like I did from chapter 4 to chapter 6, and we will come back to chapter 5 after we've learned the schematic. So that's what this lecture is about. We're putting together all the pieces, all the circuit components into one unified thought process. Okay, so we're going to just talk about, this will be a review from the intro course, types of machines, equipment. You've got a table telescoping with a drawer in it, the Bucky tray, um, and then you have a standing image receptor holder, a standing or a vertical Bucky. Um, Talk about an overhead crane. That's our most common iteration. We're briefly going to talk about um, capacitor discharge machines at the end because they do have a different schematic than this standard schematic that we run through. Incoming line current characteristics, I actually touched on that briefly in the last lecture talking about the line compensator. So I'll fully explain the line compensator, and it's basically just two components, but it does a very important job. Basic components of the main and filament X-ray circuits, and we looked at those. We did like one slide at the end of the transformer and rectifier lecture to show you the illustration of the entire schematic and kind of draw the boundary lines in between the control console, which is also the low voltage circuit, the filament circuit, and the high voltage circuit. And so we'll reiterate those points again. And then lastly, talking about either battery operated or capacitor discharge mobile units. Okay, so let's start out by figuring what is it we want the X-ray tube to do. Yeah, we want to make X-rays. What does the circuit have to provide so that the X-ray tube can make X-rays? And then we not only want to make X-rays, but we want to make X-rays efficiently, right? We want X-rays that we know their average energy. So we have to have a dialed up voltage. We need to know how many X-ray photons we're sending in the beam. So we need to have a way to set the tube current. Yeah, those type things. Okay. And I think I have some animations here. Yeah, we need a source of electrons because the electrons are what makes the X-rays in the tube. Okay. Those would be the excited electrons at the cathode filament via the thermionic emission that I mentioned at the tail end of the last lecture. Okay? We also need a force to accelerate those electrons to high speed. That is the push or the pull on the electrons. It's the sum of all Coulomb forces acting on the electrons. That is the kilovoltage. Okay? That's coming to us from the step-up transformer, the high voltage transformer. We need a vacuum. Now, we can make X-rays without a vacuum, but this is efficiency. So, vacuum evacuating the inside of the X-ray tube makes it so that the electrons really don't collide into stuff that it's not supposed to collide into. If we had air inside the X-ray tube, then the electrons that we're trying to bombard against the anode might collide against random nitrogen or oxygen atoms, or even carbon dioxide, or a water molecule, whatever. You know, the stuff you find in air. And it won't necessarily make an X-ray. Sorry, interrupted by a phone call. So, yeah, we don't want the electrons careening off of random air molecules because they probably won't make an X-ray. We need a high atomic number target like tungsten to make X-rays efficiently. Okay? So the tube does have to have a vacuum inside where there's no air molecules impeding the electrons. Okay. Selectable and measurable MA tube current. So not only do we have to dial up a specific tube current, so we have a specific quantity of X-ray beam, we also need to know what we've dialed up. So we need some kind of an ammeter device. Post-exposure. Selectable focal spot size, which is unfortunately absent from the illustration in the Carlton book, but I do have some other schematics from other authors where the focal spot selector switch is located in the schematic. And again, that's an efficiency thing more than necessary for function. The kilovoltage and the source of the electrons and a target to slam into. Those are the three necessary components for X-ray. All the other stuff is efficiencies. Selectable measurable kilovoltage. Okay, so we also want consistent penetration with our X-ray beam. And so we need to be able to dial up to a specific penetration power, which we know is the kilovoltage. And we need to measure that on the circuit so we're assured that we are delivering the penetration power that we chose. Okay, so we need a voltmeter somewhere on this circuit. We need an MA meter, a milliamperage meter to measure tube current, and we need a voltmeter to report kilovolts. And so we have some idea of how much electricity is being used per each exposure. Selectable exposure time, very, very important. We want to make X-rays, but typically if we want to avoid motion on our image, one of the best universal applications that we can, or tactics that we can employ, is to create exposures that are very, very rapid. That is, it's over with nearly instantaneously. Super short exposure times don't allow for patient motion, either voluntary or involuntary. And so we get a better image quality with less motion. Less motion means better spatial resolution overall. Coffee, warmer, hot plate. This is a joke. You're not allowed to have You are not allowed to have personal beverages and food items in clinical areas. But I don't know, a coffee warmer hot plate that would be kind of handy on an X-ray machine. Just saying. Guess when I build my after society collapses and I build my own X-ray machine in my garage, it's definitely having it's going to have a coffee warmer. Okay. Um, Types of X-ray equipment: diagnostic and therapeutic. Therapeutic, we will talk about. That's a whole nother class. We'll talk about that in imaging equipment next fall for my students. Diagnostic, typically you're going to have tube currents between 10 MA and 1200 MA. Exposure times: 10 seconds is generous, 5 seconds is an eternity for an X ray exposure. Um, but all the way down to 1/1000th of a second. That's for the modern equipment, that's pretty good actually. And then 25 to 150 kVp. That depends on the manufacturer. A lot of these depend upon the manufacturer and basically the bulk of the generator. What is the high voltage transformer? What's its maximum potential? That's your upper limit to your kVp. Just about every machine can deliver low kVp. It's how high can you crank the generator varies significantly from manufacturer to manufacturer. And of course, if you buy the one that's capable of 150, it's usually going to cost you more. So, um, honestly, in my experience, I think I might have shot maybe 2 or 3 exposures in my 15-year career that were greater than 130 kVp. Um, we only had one piece of equipment that could do it. The Siemens fluoroscope. It was a Sirescope model, had a 150 kV generator. I've never seen a GE machine go north of, to my recollection, north of 130. So they usually top out either 120 or 125. So um, honestly, there's not much difference between, unless you're talking about an extreme hypersonic person, and even then, the amount of scatter radiation you're generating, 130, 150. If it's not going to be penetrated at 130, you're not really going to see it better at 150. You really aren't, because you're generating so much scatter at that point that it's virtually non-diagnostic. So 150 is a little bit extreme as far as what you need for most folks. I've ever, again, I can count on one hand the number of times I went north of 130 kVp for a technique. So, all right. So yeah, that's our capacities for our generator and our timing circuits, um, and for our tube current. Tables: uniform radiolucent surface. Okay, so um, not sure when particle board was invented. Different from plywood. Plywood is still one tree, but some genius somewhere figured out, hey, all this sawdust, we can press it into a loaf and make it into a panel of wood. And so that's where particle board comes from. And a lot of the plywood you see now is pressed scrap, shavings of plank lumber and sawdust. Just put a little glue in there and just press the snot out of it, and it turns into a facsimile of wood. Okay. And so a lot of your older tables are particle board. Newer tables are going to be um, durable, like rigid construction polymer plastics, or carbon fiber. Carbon fiber is getting a little expensive now. Um, Uh, the advantages of carbon fiber when it first came out was it was structurally is had the same structural support strength as the equivalent thickness of steel, but it was lighter weight and cheaper to make than steel. And then it caught on, and the carbon fiber manufacturers said, "Hey, you know, we could just charge double what we used to." And so now we're seeing a lot of polymer plastic tables rather than carbon fiber um, surfaces. But both of those are excellent options, and you still see pressed sawdust tables, the particle board tables. Um, is one of them more radiolucent than the other? I think it's about a wash, really. I don't think it makes a great deal of difference whether you're X-raying on a old particle board table versus a new plastic table. Um, just as long as it's a radiolucent material, X-rays, what you don't want is a stainless steel X-ray table. Okay. Flat surface is most common. Um, yeah, Philips did a weird thing where they had like raised um, edges down the longitudinal edges of the table. Yeah, that was not a good idea. It was an uneven work surface. When you try to do extremity work, that raised edge always gave you fits because you couldn't lay your cassette flat. It was always canted and sloping from left to right. So a flat surface is ideal. We do want it wide enough that it can support a stretcher mattress at the very least, all the way up to I'd like to be able to balance a hospital mattress on it, not necessarily the same width as a hospital mattress, but I'd like to be able to slide. If I do have a hospital bed, that the mattress can slide off of the chassis and onto my exam table, I would like the ability to do that. Okay. Flat surface is just, I mean, it's just, that's the best design. It really is. Four-way tabletop motions. Yes, you should have a free float type design such that you click it like a toggle switch, and it allows you to move the surface of the table up and down, left to right, back and forward, so on and so forth. Now, the up and down motions, that's not part of the four-way floating tabletop. That's usually a motor in the telescoping base that is raising and lowering a piston or like a rack and pinion gear drive. Um, must be easy to clean, so let's not do a textured pattern. Let's just do a flat countertop like surface, because textured patterns, um, while they'll probably hold the patient to the table a little bit better and prevent some of those falls, they're also going to be fomites. So any textured surfaces are right out because the cracks and crevices of the texture are going to hold on to your MRSA, your VRE, your rhinovirus, and basically any of the uh, infectious pathogens your first patient brings in. Some of them will be left on the textured surface. So let's just have a smooth surface, no scratches, no stippling, no porous areas to it, free of crevices that could collect contrast media and patient sweat and other body fluids. And then difficult to scratch. A scratch resistant coating um, on the top of the table would be appreciated, okay, because techs are rough with the equipment. And then, of course, it's going to have a bucky tray, and inside the bucky tray, you're going to have an oscillating grid. And then the bucky tray should receive a standard 14 by 17 image receptor. The other type of table, if you don't have a variable height table, like a conventional X-ray telescoping table, Then you're going to have a tipping table, and that's usually in your fluoroscopy suite. Yeah, this is the exact design that I was fussing about earlier. You see those silver stripes running down the side? Those are actually about a quarter of inch raised from the beige area. Now, I understand why they did that because um, we used to call these things barium traps. And so they made like little curbs on the edges of the table so barium wouldn't run everywhere. It would kind of stay in the beige area. And so you had like little berms, the little silver berms on the side. And you could hold, I don't know, about a half inch thick puddle of barium in the middle of the table, and it wouldn't make a mess and drip down into the underside of the table, which could become problematic. And it's um, also a fomite hazard because I bet you that barium is used. Okay, so your tilting table uh, has the ability to stand upright, which is very useful for esophagograms and other fluoroscopic procedures. Uh, if it stands upright, it typically also goes Trendelenburg. That's a maneuver that's required for some of the myelograms is a Trendelenburg tilt. Also, for the Valsalva maneuver to test for hiatal hernia GI reflux, you need to tip the patient Trendelenburg. And so typically that is a function of the tilting table is it goes Trendelenburg, some as much as um, it looks like 90 degrees Trendelenburg. No one's going to do that. Uh, I think the steepest I've seen Trendelenburg uh, capacity is 45 degrees. 90 degrees, no one's going to tip a patient 90 degrees upside down on their head. It's just too risky. Um, but then standing upright, it goes to a full standing position. Footboards are usually an attached piece that lock into the table surface by basically spring-loaded um, buttons, so to speak, or pegs. Um, Make sure that your footboard is securely attached before you have your patient go for a carnival ride and experiencing the 90-degree tip. Okay. Shoulder supports and hand grips. Occasionally, you're going to need those. Like I said, for cervical myelography, you're going to need the shoulder supports and compression bands. Back in the day when we did IVPs, you might be utilizing compression bands with your fluoroscope, maybe even for a small bowel study. So, different accessory equipment for different procedures. Very straightforward. Tube supports. Okay, so overhead three-dimensional crane, which means that you can move it longitudinally, you can move it transversely, you can move it vertically. Oh yeah, it's the one we do use for lab, right? Okay. The overhead crane is probably, as far as a fixed room, the overhead crane is usually the most versatile as far as being able to do the greatest variety of projections and such. A floor to ceiling post mount or a floor mount x-ray tube has got a little bit more limited capacity. You can't do much stretcher work with that because the x-ray tube is always over the exam table. So whereas a crane mount, you can leave if the patient's arriving by stretcher and it's a tabletop exam, you don't have to move the patient to the exam table. You just do the x-rays with the patient in the stretcher with that overhead 3D crane, the ceiling crane. But if it's mounted like on a vertical post on the wall on the far side of the table, you got to move every patient to the table basically. Okay. Floor mounted, similar to a floor to ceiling mount. Again, it's on the wall. It's on one of the walls. It runs on a little railroad track up and down that wall, but you can't really come out into the room with it with the freedom you have with the overhead crane. Okay. Um, Mobile X-rays are even better than the overhead crane as far as flexibility of manipulating the tube. It is a different design. It's kind of like the floor mount design, but the floor mount is now on a set of wheels, and so you can move the wheeled base around anywhere you want, and then pivot the tower and sling the tube anywhere you want from there. So the mobile X-ray machine actually is more versatile with the number of things you can pull off with it than the overhead 3D crane, because you can drive it into a whole separate room if you need to. So, um, yeah. And then the C-arm. C-arm is mobile fluoroscopy, and it really is made for invasive procedures and surgeries. Um, I have utilized one personally in assisting an orthopedic surgeon in um, reducing a dislocated shoulder. That was not an invasive procedure. It was a closed reduction where they just pulled traction and popped the humeral head back in place. Um, but the C-arm is really like when you need fluoroscopy portably. Most commonly surgery, you do see it in other applications. Um, I don't know if this is a read on the economy or what it is, but some locations I'm familiar with have been substituting the C-arm for the fluoroscope because the fluoroscope broke and we either can't get the parts or it's not in the budget to get it repaired or to replace the room. And so we just moved the C-arm into the fluoroscopy suite. Now the C-arm is doing the duty of the fluoroscope, the stationary in-room fluoroscope. So, which it's totally capable of doing. All right. Upright receptor units. Um, we call this the vertical bucky. It does have a oscillating grid. Okay. It'll have AECs. Your table will have AECs. May include AECs. I've never seen a vertical bucky that didn't have AECs. Okay. Of course, it goes up and down. This is for upright exams, notably a chest x-ray, but other upright exams as well. Any of your standing lower extremities for orthopedics can be done at the vertical bucky. The older units will typically not tilt, but the newer units will, especially if they're like digital units. Um, Probably built in the last 5 to 7 years. Um, you can tilt the vertical bucky into a tabletop, okay? And then you can do a wide variety of exams. If you remove the grid from the vertical bucky, then you can do hands, wrists. You can even, if you can get it low enough, you can do feet and ankles from the vertical bucky with it tipped into a horizontal. It's just a handy feature to have a tipping vertical bucky. Not all of them do it. You have to, you know, buy one with those bells and whistles on it. Okay. Right. And then specialized diagnostic equipment, your mammography, your tomography, your CT machine, but also some of the X-ray tubes do have a tomographic function. Your dental panoramic, which is also that is a tomogram, but it's a unitasker. It can only do one. It can only do the mandible typically. Um, and then radiation therapy simulators. That's typically a CT scanner with some special software included. And then your urologic machine, which is it's a fluoroscope, but it's inverted. So a conventional fluoroscope, the X-ray tube is at your ankles when you're operating it. It's underneath the patient, underneath the table. and the image receptor is above the patient. But in a urology fluoroscope, the X-ray tube is above the patient, and the image receptor is under the table. Okay, and the reason is the urologists like to put on a tube angle every now and then, and a conventional fluoro tower doesn't allow for axials. Okay, but a urologic fluoro tower does allow for axials. All right, so now that we've reviewed the types of equipment, now we're going to launch into the basic X-ray circuit. Okay, so there's the main X-ray circuit. Well, this textbook calls it the main X-ray circuit. That would be the top circuit. Typically, there's the top circuit and the bottom circuit. The top circuit is your kilovoltage selection, and the entire point of the top circuit is to set and measure kVp and time. Okay, your exposure switch is also on this circuit. Okay. The exposure switch literally determines whether you're sending electricity to the high voltage transformer. Once you send electricity to the high voltage transformer, you are sending electricity to the X-ray tube. Okay. And then the bottom circuit, the filament circuit, is part of the low voltage circuit. The high voltage, the kilovolt selection at the auto transformer is also low voltage. The timer circuit is also low voltage. Okay. The filament circuit is low voltage, but it does end up being dangerous, just as dangerous as high voltage because it's high amperage. Okay. The bottom circuit, the filament circuit. So the top circuit is measure and select kVp. The bottom circuit is measure and select tube current. Well, you actually measure tube current, but you select filament current. Okay. And so this is alternate author because I like this diagram better than the illustration that we have in the book, because this is actually using schematic symbols. You can see letter C circled with a sine wave in it. That's the source of AC power. That's AC generator. That's back to the hospital grid. The wire coming out of the wall that's heading into the breaker box right before your X-ray machine. The second symbol you see right past C is the circuit breaker. And I've showed you that. Okay. And now what they mess up is that little rectangle. That's in the wrong place for this illustrator. That's supposed to be the line monitor, but it's not wired in correctly. Okay. And then B, that is your major minor kVp selectors. Okay. Coming off the secondary side of your auto transformer. Hopefully you recognize the auto transformer in orange. Okay. And then E is what we call the pre-reading kilovolt meter. Okay, it is a voltmeter. We can tell it's a voltmeter because it's wired in parallel. And I told you, if you want to predict voltage elsewhere in the circuit, you have to wire your voltmeter in parallel. Now, what is it wired in parallel to? It's wired in parallel to the auto transformer, so it tells us what voltage we've selected. But it's also wired in parallel to our high voltage transformer. So it tells us it can, if we just adjust the scale on the meter, it can tell us the kilovoltage output at the high voltage transformer because it's wired in parallel to it. It's also wired in parallel to the X-ray tube. Now the X-ray tube in this diagram is turned sideways. I don't know why they did that. Maybe to make it harder for you to see the ladder. Okay, if you want to see the ladder, I need you to turn your head sideways, right? And then you can see the auto transformer is one of the rungs of the ladder. Where the voltmeter is at E is the second rung. And then the high voltage transformer is the third rung. And then if you turn that X-ray tube vertical, I don't know why they turned it sideways, That's the fourth rung of the ladder. So all of those are wired in parallel to each other. So the voltmeter is literally telling you the voltage at the voltmeter, but it's also telling you the voltage at the auto transformer, the voltage at the step up transformer, and the voltage across the X-ray tube. Okay. Um, Continuing on, there's a gray rectangle. That's the timer circuit. Okay. And then F is the high voltage transformer. We see the primary and secondary side. It is a step up transformer. G is the diamond rectifier. They have just, again, they have drawn it differently to confuse you, but that is the diamond rectifier or the rectifier bridge. And then the final, the oval, that's meant to be the cathode and anode of the X-ray tube. Okay. And so that's what they mean by the main circuit. I would call this control console for the first half, and then after you get past the high voltage transformer, that's the high voltage circuit. The high voltage circuit contains the secondary side of the high voltage transformer, the rectifier bridge, and the X-ray tube. Okay. All right. So getting back to the main circuit, it starts with hospital power supply. They're going to give us 60 hertz alternating current. The root mean square voltage of 200 to 240. You might recognize that as 220 plus or minus 20, which is very similar to 110 plus or minus 10. Okay, so that's what's coming from the hospital power supply, from the circuit breaker, is this 60 hertz AC wave, roughly 220 volts. Okay. That comes into the primary side in quotations because the auto transformer has only got one coil. So the theoretical primary side to the auto transformer. Okay. And looks like I've chopped the line compensator. So let me explain the line compensator to you real quick. Remember I said there's a fluctuation in voltage. You see it right here. You see anywhere between 200 and 240 incoming volts. Okay. What the line compensator does is it's another voltmeter measuring the incoming voltage and then selecting a proportional number of coils on the incoming side of the auto transformer. So if it's 240 volts coming in, then it's got a switch that includes 240 coils. And then you get the trick that I explained last time where the denominators of the transformer law disappear and it's just number of turns secondary equals voltage secondary. Okay. So, but what if the voltage dips on the line because the power company is not there? They say 220 plus or minus 20. So it could be 240 at one moment in time, and then you start the exposure, and then while you're doing the exposure, there's a dip on the line, and it all of a sudden bottoms out to 200. Well, the line compensator will adjust the number of coils that it includes by moving the multi-point switch to include less coils on the primary side. So you have 200 incoming volts and only 200 coils included on the primary side of the auto transformer. So the line compensator compensates for fluctuations in voltage and ballasts that with fluctuations of primary turns so that they're always equal to each other. Okay. Your KVP selector. You notice I'm showing you different illustrators and different basically different diagrams from different illustrators. That's on purpose. Are they going to use the Carlton illustration on the registry exam? No. Are they going to use any of these that I've shown you? No. They're going to hire a brand new illustrator to draw this from scratch and not make it look exactly like any of the textbooks. And that's why we get such variation with that's still the auto transformer there. Okay. Number 7 is still the secondary side multi-point switches to select the number of output coils. Okay. You have a major and a minor selector. Okay. We call those the major minor KVP selectors. Number 1 is still same as letter E. That's the pre-reading voltmeter. It's wired in parallel, so you know it's a voltmeter. So when we select the output turns, we effectively select the output voltage. You want 54 volts going to the high voltage transformer? Select 54 coils. You want 120? Select 120 coils. Okay, so you get to do in the major selector, you get to skip about 10 coils. I know it's not illustrated well here, but you would skip about every 10 coils. So that would be plus 10 kV, minus 10 kV every time you switch to a no point. In the minor selector, you're only skipping about 2 coils. And so that'd be plus or minus 2 kVp. And between the two, you basically dial to within plus or minus 1 any kVp number you want between 50 and whatever your generator goes up to. Okay? And again, this is because we can exploit the transformer law via the line compensator such that we're only dealing with the numerators of the transformer law. The voltage output, the voltage secondary, is going to be equal to the number of turns secondary. If we can select the number of turns secondary, we can select the output voltage. Okay. And then, of course, we're measuring that. And if we change the scale on our meter to times 1,000, we can predict what the X-ray tube is going to experience. Our exposure switch. Our exposure switch has to be a dead man switch. That is, if we're taking an exposure, and this is most important for fluoroscopy, but if we're taking an exposure and the X-ray operator, whether it be radiologist or technologist, has a heart attack or passes out or some such thing, we want the machine to stop exposing. We don't want it to continue to blast the patient with radiation if we're not consciously mashing down the button and making a conscious decision to apply the radiation. Okay, so that's what a dead man switch is. You press and hold pressure on it, the circuit's live. X-rays are being made. As soon as you release pressure, the circuit is dead. You are no longer making X-rays. Okay, it's a safety feature so that we don't get a runaway X-ray tube that just keeps exposing. Your exposure switch is supposed to be located behind the control panel on the generator console, the settings where you select KVP and mass. It's supposed to be right there next to the selections for KVP, mass, and time. And it's supposed to be in the control booth. Okay. It's supposed to have a short cord or no cord, because the last thing we want to do is give the technologist the ability to bring the exposure switch in the room. We want you to stay behind the lead barrier in the control panel or in the control booth. Okay. Now, the new thinking is depress it in one motion to maximize tube life. The old thinking was you have to get your rotor up to speed first. So you got to hit prep first, let it prep, and then expose when you're ready. Okay. Your X-ray, if you mash it is a two-phase switch. If you mash everything down at once, you won't get instantaneous X-ray. You'll get X-ray once the rotor's up to speed. It's usually about a quarter second delay, quarter second to a half second. Okay. I prefer to rotor, give the instructions, confirm that they've received the instructions, they're actually holding their breath, and then make an exposure. Okay. The the thing I hate the most is it's automatic face palm when I see a fellow technologist mash it all the way to the floor while they're yelling, "Hold your breath." And then the next two sounds you hear are beep, what? So, yes, it does extend tube life to mash it all down in one go. But there's a reason it's a two-phase switch. You're giving breathing instructions or final instructions to your patient. At the very least, hold still. And then what do you suppose that window is for? Because lead glass is expensive. Oh, yeah, you're supposed to look through it and confirm that your patient is following your instructions. If they're not, well, then get your finger off the prep button and go back in there and explain it. But if you press it all down in one motion, are you going to catch it in time? No, probably not. So, yeah, yeah, your rotor bearings do get excessive wear for rotoring for too long, but I would rather do less repeats. So, um, timing the breathing, if you're ever doing pediatric x-ray, you are going to do prep and hold on the prep phase and wait for the patient to comply, especially if they're crying. You're going to be using a timing the breathing technique. Wait for them to scream their little lungs out, and then when they take in a deep breath to give you a second round of the banshee wail, that's when you make the exposure. Okay. On mobile equipment, so on room built equipment like in an x-ray room, the exposure switch is short, so you stay behind the control panel. On mobile equipment, the exposure switch is either long or remote control. Both of these are radiation protection. We want a long exposure switch, a long cord on our portable machine so we can step out of the room because we don't have a lead barrier control booth. Okay. All right. Often not depicted on the schematic. Prep and rotor is switch on the filament circuit. So the first phase is actually turning on the filament circuit. The second switch, the exposure switch, mashing it all the way down, that's a switch on the main circuit before the high voltage transformer. It's wired in series to the timing circuit. Okay, our timer circuit regulates exposure termination. Electronic timers are our most sophisticated ones, capable of very short exposure times as low as 1/1000th of a second. Okay. Um, our mass timers terminates the exposure on a predetermined mass value. This may or may not be a falling load generator. Okay. And then our AEC timers don't measure time at all. We'll learn about AECs in the fall. AECs, the modern ones are ion chambers, so they're literally catching ionizations. When they reach threshold ionization count, then they shut the exposure off. Your electronic timers, you've used something similar if you've ever made cookies. Okay? Everyone knows that cookies can be messed up really easily if you let them go too long. So typically, like for the chocolate chip, the break you get like a loaf that's pre-cut. You just snap off little squares of cookie dough and lay them on the cookie sheet. don't fuss at me. No one makes them from scratch anymore. Um, Hang on. All right. So what was I talking about? Oh yeah, burning cookies. Don't do it. So you gotta set the cookies for 12 minutes, not 13 minutes. They get charcoal edges at 13 minutes. 12 minutes. That's it. Well, you need a timing device. Well, everyone knows that you bake things according to certain temperature, certain time. If you don't follow the recipe, you're going to end up burning your food. And burnt chocolate chip cookies are the worst. Just throw them in the trash. Okay? So, your timing device, most of your modern ovens are built with a timing device. And it uses a, LED digital readout. But what is the timing circuit made out of? Well, the same thing the electronic timing circuit in the X-ray machine is made out of. A vibrating piece of quartz. Yeah. So it's quartz timing. We've had quartz timing since somewhere in the 70s. Became available for commercial use, that is regular consumer use, sometime in the 80s. Um, but we figured out that quartz, if you pass electricity through it, it vibrates at a certain frequency depending upon how much voltage you pass through it. And so we can, since it's a known property of quartz, that it vibrates at this certain frequency at this certain voltage, then we can use the vibration of the quartz to keep track of how many seconds have passed, or fractions of seconds, like we do in the X-ray machine. Okay. High voltage transformer and the rectifier. Now, technically, only the secondary side of the high voltage transformer is in the high voltage circuit. The primary side is low voltage. Okay. That doesn't mean you want to grab a hold of the bare wire from either part of the transformer. Um, but the primary coil for the high voltage transformer is whatever you set coming off of the auto transformer. Then it gets amplified into high voltage through a step-up transformer. And then we also see tethered to the middle coil of the secondary side of the high voltage transformer this is a poor drawing, a ammeter wired in series to the coil. Okay. The middle coil has got zero magnetic field change. Go ahead. Do the little Fleming electromagnet right hand rule, right? And then take your other hand and put it between the MCP joints of the third and fourth digit. And now reverse the magnetic field. That is, flip your hand over and then flip it back and then flip it over and then flip it back. And notice that that point in between your knuckles is halfway between north and south poles of the flipping magnetic field. And then when you flip it over, it's still halfway between the north and the south poles. So there is no changing magnetic field at the very middle coil of a transformer. So theoretically, there is no high voltage there. Okay. And so that's why it's safe. That is the only part of the high voltage circuit that wires back to the control panel. That is the tube current ammeter wired in series to the coil, but also to the X-ray tube. Okay. And it is grounded out too, just in case the theory about not really high voltage doesn't work out. Okay. So number 2 here was the high voltage transformer. Number 3 is our tube current MA meter. Number 4 is our rectifier. Do they have that running right? Let's see. What positive charges to go there? Negative charges. Yep. And then coming off the bottom, I want positive charges. Yep. Yeah, they do have it drawn right. Good. Okay. And then finally, that's the X-ray tube in parallel. Now you can see that the X-ray tube is running parallel to the secondary coil of the transformer through the diode, but still in parallel. All right, here's our filament circuit. This is a static takeoff from the auto transformer over here on the far left. So that means we have a fixed output voltage rather than a variable output voltage on this bottom circuit. Okay, and then we're going to head into the rheostat where we manipulate Ohm's law at part D. That is our rheostat with a multi-point switch. Okay, and so we got a fixed voltage and a selectable resistance. So Ohm's law says whatever change in resistance we apply to this voltage, it's going to have an inverse. The higher the resistance, the lower the output current from the rheostat. Right after the rheostat, you see a switch that divides the step-up transformer into an upper half and a lower half. That is our focal spot selector. We can either power up the large filament in the cathode or the small filament in the cathode from that switch in between D and H, but not both at the same time. And so that effectively kills the power to half of the step down transformer at H, the filament transformer. And so therefore only the top half has an induced current or the bottom half has an induced current, but not both at the same time. And so only one of the filaments receives electricity at a time. Okay? It's a brilliant design, actually. All right. So the rheostat, variable resistor that I explained to you before, is used to change resistance in series to the filament transformer. With a constant voltage, Ohm's law states that resistance and current have an inverse relationship. So if the voltage is always 12 and I increase the resistance, the current has to decrease. If the voltage is always 20 and I decrease resistance, then the current has to increase. The resulting filament current, which is what's set at the rheostat, is adjusted by changing the resistance at the rheostat. And since it's wired in series to the step-up transformer, the output current at the rheostat is the current at the primary side of the step-up or step-down transformer. Okay. Remember, in a step-down transformer, the amperage increases. Okay. And so the filament current selected at the rheostat is amplified through the step-down transformer. Okay. And now we can see its connection to the cathode over there in the X-ray tube. Okay. And so again, we have the focal spot selector switch at the arrow. We can either power up the top of the transformer or the bottom of the transformer. And there's kind of a shared bridge wire between the two filaments. Okay. Notice the bridge also makes a T connector with the output to the rectifier bridge. The bridge connection. What a segue. Okay. So there is a bridge connection here between the filament circuit coming in from the bottom, the 3 lines that leads to the filament transformer we just talked about. But the middle line bridges, because remember the middle line is included in both the small filament circuit and the large filament circuit. The middle line bridges with the high voltage circuit. That is, there's a T junction there. So when you hit the prep switch, electrons are just going up and down the filament circuit and returning to the filament transformer. They're not going back into the rectifier because there's no voltage at the rectifier. Okay, That's during prep. So that T connection, that's basically a dead circuit. The filament circuit is a closed loop with a voltage being applied. And so you do conduct electricity there, but that's just a dead wire with the electrons are not motivated to flow down it. They're not experiencing a pull in that direction. When you press down the exposure switch, now most of the electron flow is diverted to the rectifier because the filament circuit is a low voltage circuit and the rectifier circuit is part of the high voltage circuit. So when the high voltage circuit is activated, it kind of steals the current from the filament circuit. All right, capacitor discharge units. Now that you've learned all the piece parts of the schematic, that's for a typical, let's see, that's a full wave rectified single phase. That would have been your typical X-ray machine around 1940, 1950. Okay. We've done all sorts of things since then, and you're going to learn about more efficient voltage waveforms, three-phase power, all that kind of stuff. That's coming up. Okay. We also have capacitor discharge machines. And so remember the capacitor was, I told you it functioned like a temporary battery. It trades voltage for charge. It starts building up charge in the capacitor. And then when the voltage drops on the line, the capacitor trades that stored charge back in for voltage ballast. Okay. And so it can temporarily store, we call it static voltage, is what a capacitor holds on to, which doesn't really make sense because voltage is a vector and it's got a direction. So, yeah. But it really is, it's just storing charge that is going to convert to voltage later. Okay. Now, capacitors are great because you can get away with a lot smaller components, namely your transformers. Okay. If you have an array of capacitors between your rectifier and your X-ray tube, then you can get away with a smaller step-up transformer and load your kilovoltage into capacitors without actually ever generating kilovoltage at a transformer. Okay? You can just store up charge, which would be the equivalent of kilovoltage once it's released. Okay. And so that makes for less generator space. You can get away with a smaller generator, a smaller step up tree. You will need to step up the transformer some, but not a lot. You could, I guess you could do a capacitor discharge unit that didn't have a step up transformer at all. It just had a capacitor array. But it trades out, so the voltage is not really being generated by the transformer. It's really being accumulated over time. You plug this thing in, and then you can see the capacitor meter fill up, kind of like you're charging a battery. And then when you get full green, then you know it's ready to discharge your capacitor array and shoot an exposure. And then once you shoot an exposure, you're going to bleed out most of the charge, and then you're going to have to wait again for the capacitor array to charge up. Okay. If they do have a step-up transformer, it's going to charge faster, and so you'll be able to take the exposure faster. Okay. The tricky thing about a capacitor discharge unit is the techniquing is a little different because you actually lose kilovoltage through the exposure. You start out at peak kilovoltage, but your voltage starts tapering off through the duration of the exposure. Capacitor discharge units are these X-ray machines weigh less than 50 pounds. You can prop them up on bicycle wheels. So I've actually worked with a capacitor discharge machine. It is super light. The whole thing weighs, like I said, somewhere between 50 and 100 pounds on bicycle wheels. You can push it without a drive motor. You can load it up on, if you got loading ramps, you can load it up into the back of a van. It's a very handy device for nursing homes and assisted living units. All right, so this is the load up and the charging in these graphs. You pre-charge, right? And then usually there's some kind of indicator on your control panel that goes from red to green. When it turns green, that means your capacitors are fully charged. Okay. And it's ready to expose. You got to plug this thing into the wall to charge the capacitor arrays. Okay. Um, Now you typically run with, see the bottom one, the green, the diagram B. You typically set your KVP higher with a capacitor discharge machine because you know it's going to bottom out through the exposure. You're going to lose as much as 30 or 40% of your total KVP. So if you, let's say you normally shoot a knee at 60 or 65 kVp, you're going to shoot at 85 on a capacitor discharge machine because it's going to plummet from 85 down through the 70s and it's going to finish up at about 50 kVp. But the average over the entire exposure is going to be somewhere in the 60s, you see? And so that's why you start out with a higher KVP technique than what you're expecting, is because you know with capacitor discharge your KVP plummets while the exposure is going on. Okay. All right. So that was the X-ray schematic. Okay. Um, a lot of, like I said, a lot of the context of what is this part doing, what is that part doing. While I explained to you the different circuit elements, I already told you what their function was. So now you just have to take a picture of the whole schematic. And don't worry, if you're in my physics class, I'm going to give you a couple homework handouts with full schematic diagrams that you'll have to label both what's this part, what's that part, and then what also does it do. Okay. And so just because chapter 6 in the Carlton book does talk about the various types of X-ray equipment, various standard accessories like a table and a vertical bucky, and then like how is the tube supported, so I included those slides in here for continuity with the book. But really what I'm going to ask you about is the parts of the schematic and their function, their names, things like that. So that's what's coming up on the test for this lesson. So hope you enjoyed it, and on to the next one.